In this video, we're going to talk about the calculus of vector-valued functions. So just like with ordinary functions, we can talk about limits, derivatives, and integrals of vector-valued functions. And the way that we do each of these is component-wise. Okay, so I'll explain what that means in a second here. So basically the idea is that you do, if you want to find a limit of a vector value function, you take a limit within each of the components. If you want to find a derivative, you take a derivative of each of the components and so forth. Okay, so let's let r of t be this vector valued function. T squared plus 3i plus e to the tj plus sine t over t k. That's supposed to say k. Okay, or we could write this one in the bracket notation like this. Now let's find r of 2. Okay, how do we find r of 2? Well, we'll just replace each of these t's with 2. So we're going to get 2 squared plus 3. Okay, that would be 7. And then we'll have e to the 2, so e squared, and then sine 2 over 2. So r of 2 is just this vector right here. Okay, now what's r of 0? Well, r of 0, we do the same thing, only notice what happens in the third component here. We get sine 0 over 0, which is undefined. That's 0 over 0. So in other words, r of 0, even though it is defined in the first two coordinates, the vector as a whole is undefined because it's not defined in the third coordinate. So in other words, 0 is not in the domain of this vector valued function. Okay, but r of 0 is not defined, but what about r of t if we let t approach 0? So in other words, what's the limit as t approaches 0 of r of t? Okay, so r of 0 is undefined, but we can look at r of t and let t approach 0. Okay, so that's what we're going to do. So how do we do this? Well, we take the limit within each of these components. The limit as t approaches 0 of t squared plus 3. Limit as t approaches 0 of this and of this. Now notice in the first coordinate, we're just going to get 0 plus 3 is 3. Then e to the 0 is just 1. But what about this last one? What's the limit as t approaches 0 of sine of t over t? Well, we could use L'Hopital's rule, right? Because we have a 0 over 0. If you do that, you'd have the limit as t approaches 0 of cosine of t over 1. But remember, cosine of 0 is 1, so you get 1 over 1, which is 1. Okay, so even though r of 0 is undefined, the limit as t approaches 0 of r of t does exist. That limit exists. So this is the vector. Okay, now what's r prime of t and what's r prime of 1? Okay, so here's r of t. What's r prime of t? Well, take derivatives within each of the components. So r prime of t is going to be 2t. Okay, comma, well, the derivative of e to the t is e to the t. And then how do we do the derivative of this? We're going to use the quotient rule, right? Low d high minus high d low all over low squared. Okay, and if you work that out, right, the derivative of the t squared is going to be 2t. Derivative of e to the t is, or t squared plus 3 will be 2t. Derivative of e to the t is e to the t. And the derivative of this, we do low d high, so t times cosine of t, that's the derivative of sine, minus the high d low, so minus sine of t times 1, right? The derivative of the low is 1. And then over t squared. So there's r prime of t. Okay, now notice that if r of t is a vector valued function, r prime of t will be a vector valued function as well. So kind of like if f of x is a function, f prime of x will be a function, right? If f of x is x cubed, f prime of x will be 3x squared, right? So the derivative of a function is a function. Well, the derivative of a vector valued function is a vector valued function. Okay, now what about, oh, by the way, there's a couple different notations for r prime of t. You could also write it as dr dt or d of r of t dt. And that t should not be bold there. But okay, so we have a couple different notations for the derivative, just like we do for ordinary functions. Okay, now what about r prime of 1? Okay, we have r prime of t. What's r prime of 1? Well, we already found r prime of t was this vector valued function. If we plug in 1 for t, notice what we get. We're going to get 2 comma e to the 1 comma, well, this ends up being cosine of 1 minus sine of 1. Okay, but the point is this is a vector. So in other words, the derivative of a vector valued function is a vector valued function, but the derivative at a number ends up giving you a vector. Okay, now that's a little bit different for functions. So notice we get a vector, not a number. So for ordinary functions, if like f of x is x cubed, the derivative would be 3x squared, but the derivative at 5, right? So f prime of x would be 3x squared, but f prime of 5 would be 3 times 5 squared, so that'd be 3 times 25 is 75. So the derivative at a point of an ordinary function gives you a number, but the derivative at a point of a vector valued function gives you a vector. Okay, so r prime of t is a vector valued function. R prime of 1 is a vector. Okay, now what does that vector represent geometrically? So geometrically, what does r prime of 1 represent, or r prime of t naught for any specific value of t naught, so r prime of 5, let's say. Okay, it turns out it's a vector that's tangent to the curve at t equals 1 or t equals 5 or whatever your number is. Okay, so suppose we have a vector valued function. Now, I've drawn this in 2 space, but you could also draw this in 3 space. We have this vector valued function. Let's say it's being traced out this way, different values of t. So maybe t equals 0 gives you this point, t equals 1 gives you this point. It's really this vector. T equals 2. Maybe t equals 5 gives us this, and then t equals 6 is over here, t equals 7. Different values of t are giving us different points or different vectors, right, along this curve. So r of t naught would be this. So maybe r of 5 is this. R prime of 5 will be a vector that's tangent to the curve at that point. Okay, so r prime of 5, or r prime of 1, whatever it is, r prime of 5 would be a tangent vector. Now, how do we know which way the vector's facing? By the way, this is the tangent line here to the curve at that point. How do we know which way the tangent vector is facing? Well, if the curve is being traced out this way as t increases, the vector is going to be pointing in this direction. If the curve were being traced out this way, the vector would be pointing in this direction. Now, you might wonder, how long is that curve? And we'll talk a little bit more about this later, right? Or how long is that vector? So if the curve is being traced out this way, I know the vector is going to be pointing this direction, but how long will it be, right? The tangent vector. Why is it not way longer or shorter? Well, it turns out that it depends on how fast the curve is being traced out. Okay, the speed of the curve essentially is going to be the length of this vector. So for example, let's say this is t equals 5. If t equals 0 gives us this point, t equals 1, t equals 2, t equals 3, t equals 4, t equals 5, t equals 6. So notice it's kind of being traced out pretty slowly. Well, the tangent vector won't be very long here. On the other hand, if like t equals 0, 1, 2, 3, and then t equals 4 is here, t equals 5 is there, t equals 6 is there, it's being traced out really fast for it to go from 4 to 5 to 6. Then the tangent vector would be longer. Okay, now it turns out, and we'll talk about this in a later section, that the length of the vector is actually the speed at which the curve is being traced out. Okay, so but r prime of t naught will be a tangent vector at r of t naught. Okay, so find a vector value, or for a vector value function r, how can we find an equation for the tangent line at t equals t naught for some value of t naught? So maybe t naught is 1 or 5 or whatever. Well, let's look at this picture here. And this is my notation. This is the book notation. Let's forget the book notation for a second. So I'm going to use L of t for this tangent line. So here's our vector valued function, this curve being traced out this way. If this is r of t naught, r prime of t naught will be this vector here, okay, facing this direction. So what's an equation for this tangent line? Well, we're going to call the tangent line L of t. And L of t is going to be r of t plus t times r of t naught plus t times r prime of t naught. So for example, if t is 1, okay, what's L of 1? Well, notice these are t naughts and that's a t. Don't confuse those here. T is different than t naught. So think of t naught as being a specific fixed number here. And the t naught's sort of the variable. But what if we let the variable be, let's say, 1? Okay, well, we have r of t naught plus 1 r prime of t naught. That would get us to this point right here. Okay, if the t was 2, we'd have r of t naught plus 2 of these r primes. So we'd be at a point over here. Or if the t is 3, we'd have r of t naught plus 3 of these r prime of t naught. So we'd be at a point way over here. Really the vector that goes from the origin to that point. Now if t was 0, we'd have r of t naught plus 0 times r prime. So we'd have this r plus 0 of these vectors, meaning we'd be at this point. If t were negative 1, we'd be facing off in this opposite direction. If t were 1/2, we'd be here. Different values of t are going to give you different points along this line. Okay, so the tangent line L of t is given by r of t naught plus t times r prime of t naught. Okay, now the way the book does this, they let r naught be r of t naught. So they just call r of t naught r naught. And they call r prime of t naught v naught, and that's v sort of stands for velocity, because that's really what r prime is going to be. Again, we'll talk about position, velocity, acceleration later, but r prime of t naught is what they'll call v naught, really for velocity. And then the t stays the same, but instead of calling this L of t, they call it r, but it's really r of t. So they've kind of suppressed some things in here. But as I don't really necessarily like the book notation, I kind of prefer mine. But I want you to at least see this so you recognize what the book is doing here. Okay, so let's look at an example. So find parametric equations for the tangent line to the circular helix, x equals cosine t, y equals sine of t, z equals t, at t naught, so at some generic value of t naught, and then use the result to find parametric equations for the tangent line when t naught is pi. Okay, so different t's are going to give us different points along this curve, right? So we get a vector valued function here, really, cosine t, sine t, t. Okay, and then the question is, at a particular point along the curve, what's the equation of the tangent line? So maybe we're right here. Okay, say we're at this point along the curve. Okay, the tangent line will be going this way. Okay, and the question is, what's an equation? Okay, what are parametric equations for that tangent line? Now, if you're at a different point, let's say you're right here at pi, and we're going to ask about this pi in a second, the tangent line will look something more like this. Okay, if we're at this value right here, the tangent line will look something more like this. Okay, just for a generic value of t naught, what are parametric equations for the tangent line? And then specifically when t naught is pi. Okay, well r of t is this. Okay, that's our circular helix, the vector value function for a circular helix. So r of t naught, we just plug in t naught for each of these t's, and that's what we get. Now again, the book calls that r naught. Okay, so r of t naught is this. Or r naught is this. Now r prime of t, so if this is r of t, r prime of t is, well, take the derivative of each of these component-wise. Derivative of cosine is minus sine, derivative of sine is cosine, derivative of t is 1. And then r prime of t is that. What about r prime of t naught? Well, plug in t naught for each of these t's, and this is what we get. And again, the book calls this v naught. Okay. All right, so our vector valued function or for equation for the tangent line is going to be L of t equals r of t naught plus t times r prime of t naught. That's what we said right up here. Okay, that's just this equation rewritten again. Okay, so let's plug things in. What was r of t naught? Well, r of t naught was this. Okay, that's what we put here. Plus t times r prime of t naught. What was r prime of t naught? That's this. That's what I put here. Okay, now I can combine these here. By the way, you can distribute the t here. You can do that scalar multiplication here. So multiplying the t, you're going to get minus t sine t naught plus, or comma, t cosine t naught, comma, t. Okay, t times 1. Okay, and then you can take that vector plus that vector, and you're going to end up with this. So you're going to end up with cosine of t naught plus, or actually minus, t times sine of t naught, and then sine of t naught plus t cosine t naught, and then finally t naught plus, well, t. Okay, so notice that's a vector valued function for that equation of the tangent line, but we could think of this as being, this is the x, and this is the y, and this is the z. So those are parametric equations for the tangent line to the graph at any particular t naught. So let's suppose we let t naught be pi. Okay, so we're specifically at this point here. Now, I'm not sure why they drew that red line in there. I think that's just because saying it's on the exact opposite side here as t equals 0. So we've gone around 180 degrees. We've gone all the way to right there. And the question is, for this tangent line right here, what are parametric equations for that tangent line? Okay, well, let's plug in pi for t naught. Okay, now we're not plugging in pi for t. Okay, it's very important that you leave the t as the variable. You're plugging in pi for t naught. Now remember, cosine of pi is -1 and sine of pi is 0. So when we plug things in, we're going to x equals cosine of pi, okay, which is -1, minus t times sine of pi. Now sine of pi is 0, so this is just x equals -1. Now y would be sine of pi, which is 0, plus t times cosine of pi, which is -1. So you're going to get 0 minus t, or in other words, just minus t for the y. And finally, if we plug in pi for t naught here, we get z equals pi plus t. Okay, so these are the parametric equations for the tangent line to the graph when t is equal to pi. Okay, now we can also talk about antiderivatives or integrals of vector valued functions. So an antiderivative of a vector valued function r of t is a vector valued function capital R of t that has the property that the derivative of the capital R equals the lowercase r. Right? That's just the definition of antiderivative here that we're giving. So we write that the integral of this r of t is this big R of t. Now plus c, this is plus a constant, but it's actually not a constant number, it's a constant vector. In fact, it wouldn't even make sense to say a vector valued function here plus a number, right? You can't add a vector plus a number. It would have to be a vector plus a vector. So the c is really like a c1i plus a c2j. Okay, so let's look at this integral here. What's the integral of the antiderivative of 2ti plus 3t squared j dt? And you could write this in bracket notation, the integral of 2t comma 3t squared. Okay, dt. Okay, so we do it component-wise. So the integral of 2t is just t squared, so we have t squared I, plus the integral of, well, 3t squared is going to be t cubed, okay, comma j, and then don't forget our plus our c, okay, or c1i plus c2j. And by the way, we can combine these. We have a t squared I plus a c1i, so that's a t squared plus c1, that quantity times I, and then we have a t cubed plus c2, that quantity times j. Now, by the way, the c1 and c2 don't have to be the same constant. The point is, though, no matter what c1 and c2 are, no matter what those numbers are, this, if you take the derivative of this vector valued function, okay, for no matter what this number is and this number is, if you take the derivative of this, you're going to come up with this vector valued function. Okay, now let's do another example. So find r of t such that r prime of t is this. Okay, but also so that r of 1 is 2 comma 5. Now this r of 1 equaling 2 comma 5, that's going to tell us what our constant c is, or the c1 and c2 are. Okay, so we want to find essentially the antiderivative of 3 comma 2t. Okay, so if we're given r prime of t is 3 2t, r of t will be the integral of that. So the integral of 3 would be 3t. Now we're going to put plus c1. Okay, and the integral of 2t is going to be t squared, and we'll put plus c2. Okay, so r of t is going to have this form. Now, we also want r of 1 to be 2 comma 5. So if r of 1 is 2 comma 5, that's going to fully determine what the c1 and c2 are. Okay, so how do we find the c1 and c2? Well, we have r of t here is this. So r of 1, plug in 1 for t. We're going to get 3 plus c1, comma 1 plus c2. We plugged in 1 for t. And if 3 plus c1 and 1 plus c2, that's r of 1. Well, remember, r of 1 had to be 2 comma 5. So 3 plus c1 is going to be 2. So what that means is that c1 is negative 1. And 1 plus c2 is going to have to be 5, so c2 will be 4. So we can plug that in here. So r of t is 3t minus 1, okay, comma, t squared plus 4. By the way, check this answer. It's real easy to check, right? Is the derivative of this 3 comma 2t? Yeah, the derivative of this would be 3 comma 2t. Is it true that r of 1 is equal to 2 comma 5? Yeah, plug in 1 for t. r of 1 will be 2 comma 5. Okay, so it's pretty easy to check your answers. So this second condition really told us what the c1 and c2 were. Okay, now we can also do definite integrals of vector valued functions. So the integral from a to b of some vector valued function. Now I've written it in bracket notation here. X of t, comma y of t, comma z of t. Well, the way you do this is component-wise. You just do the integral from a to b of x of t dt, comma, the integral from a to b of y of t dt, and so on. Okay, now it's not hard to show that a version of the fundamental theorem of calculus holds. So if r of t is an antiderivative, if big R of t is an antiderivative of little rt, then the integral from a to b of little rt dt is that big R, that antiderivative, evaluated from a to b. So you plug in b for t and plug in a for t and subtract. Okay, so let's evaluate this. And we're going to kind of do it two different ways. What's the integral from 0 to 2 of this vector valued function? Okay, well, we can do the integrals within each of the components. Okay, so we do the integral from 0 to 2 of 2t dt, and I'm using the ij notation instead of the bracket notation here. But then we do the integral from 0 to 2 of 3t squared dt j. Okay, well, the integral of 2t is just t squared evaluated from 0 to 2, so we're going to get 4 minus 0, I, so that's 4i. And over here, the integral of 3t squared is t cubed evaluated from 0 to 2, so we're going to get 8 minus 0. Okay, 2 cubed is 8. So that would be 8j. So we get 4i plus 8j. So notice our final answer of a definite integral of a vector valued function is not a number, it's actually a vector. Okay, now another way to do this, though, would be to just do the antiderivative of this whole thing right away. So the integral of 2t would be t squared, so we have t squared I, plus 3tj, and then plug in the 2, evaluate it from 0 to 2. So plug in the 2, you get 4i plus 8j, minus what you get when you plug in 0. You get 0i plus 0j. And if you work that out, subtract it, you get 4i plus 8j, the same thing. Okay, so there's a couple ways that you can do it. But again, your final answer is a vector, okay, not a number. Okay, now consider the following two product rules for derivatives of dot products and cross products of vector valued functions. It turns out that just like we have a product rule for the derivative of like f times g, right? A function f times g. If we want to take the derivative, we have to use the product rule. Well, we have a similar product rule for dot products and cross products. So if we have r1 of t and r2 of t, those are vector valued functions, the derivative of the dot product, and by the way, r1 of t dot r2 of t, that's going to be a vector valued, I'm sorry, that's actually going to be an ordinary function. I'll show you that in just a second. If r1 of t is a vector valued function, r2 of t is a vector valued function, the dot product will be an ordinary function. Okay, so what's the derivative with respect to t of that? Well, it turns out it's equal to r, the first function, times the derivative of the second, plus the derivative of the first times the second. And by the way, I said times, but I really mean dot. Okay, we're taking a dot product here. And by the way, there's a similar one for cross products, the derivative of r1 cross r2. Now, these r1 and r2 have to be vectors in 3 space. Remember, you can only talk about cross products if you're in 3 space. This top one works whether you're in 2 space or 3 space. Okay, but the derivative of r1 cross r2 is going to be r1 cross the derivative of r2 plus the derivative of r1 cross r2. And it really matters the order. You can't flip these around and do like this one here and do r2 cross the derivative of r1, because that would give the negative of this. Okay, so you have to make sure you do it in the right order when you're doing the cross product one. The dot product doesn't matter because u dot v is the same as v dot u. But remember, with cross products, u cross v is actually the negative of v cross u. So make sure you do these in the correct order. Okay, now if r1 and r2 are vector valued functions, then just like I said, r1 of t dot r2 of t is an ordinary function, whereas r1 of t cross r2 of t is a vector valued function. So let's do a specific example and this will become pretty clear. So let's let r1 be this vector valued function and r2 be this vector valued function. Let's find r1 dot r2 and r1 cross r2, and then verify that the first equation above, that first product rule, holds for r1 and r2. So we're going to verify that this holds, okay, for this particular r1 and r2. Okay, so let's do this. What's r1 dot r2? Well, r1 is this and r2 is this. So how do we take the dot product? Well, we're going to do 7t times t squared plus 1. Okay, that's what we've written here. Plus sine t times t to the 5th plus e to the 4t times 3. So this times this plus this times this plus this times this. If you work this out, so you distribute the 7t, you're going to get 7t cubed plus 7 plus t to the 5th times sine of t plus 3 e to the 4t. Okay, now notice there's no i's or j's or anything. There's no commas to make this a vector, have anything to do with vectors here. This is just an ordinary function of t. Okay, the original r1 and r2 were vector valued functions. This is just an ordinary function of t. Okay, now what about r1 of t cross r2 of t? Well, remember, to do the cross product, we do this determinant of this matrix. So we're going to put ijk across the top. r1, remember, was 7t sine t e to the 4t. r2 was t squared plus 1 t to the 5th time, comma 3. Okay, so let's do I times the determinant of this. So it'd be sine t times 3, or 3 sine t, minus e to the 4t times t to the 5th, or t to the 5th times e to the 4t. Okay, that thing minus that I. Okay, and then minus the certain determinant times j, and then plus a certain determinant times k. You can work it out. Turns out this is what you get. But notice what you end up with here is a vector valued function, right? We don't just have a bunch of t's here. We not only have the t's, but we have something I, some function of ti, plus or minus some function of tj, plus some function of tk. So this is a vector valued function. Okay, so the dot product of two vector valued functions is an ordinary function. The cross product of two vector valued functions is a vector valued function. Okay, now let's go ahead and verify this product rule here. Okay, that says the way you take the derivative of a dot product, r1 dot r2, is to do r1 dot the derivative of r2 plus the derivative of r1 dot with r2. Okay, so let's do that here. So remember, we actually found r1 of t dot r2 of t. We already found that was this. Okay, so if we wanted to the derivative of r1 dot r2, we could just find r1 dot r2 and take the derivative, and that's what we're going to do here. The derivative of this whole thing, what do we get? Well, the derivative of 7t cubed is 21t squared. Derivative of 7t is 7. The derivative of t to the 5th times sine t, you're going to have to use the product rule, okay, to get this. T to the 5th times cosine t plus sine t times t to the 4th, or 5t to the 4th. And then the derivative of 3 e to the 4t is going to be 3 e to the 4t times 4, okay, which would be 12 e to the 4t. Okay, the point is that we did r1 dot r2 and we took the derivative. Okay, now what about the right-hand side, right? So we've shown what the left-hand side is here. Now what is the right-hand side? Let's figure that out, and let's check to see are those the same thing. Okay, so the right-hand side of that equation was r1 dot the derivative of r2 plus the derivative of r1 dot r2. Okay, now r1 was just this. Now what's the derivative of r2? Now remember, r2 was this. So the derivative is going to be 2t 5t to the fourth 0. Okay, that's what I've written here. 2t 5t to the fourth 0. So there was r1 dot the derivative of r2. Plus, now what's the derivative of r1 dot r2? What's the derivative of r1? Well, the derivative of r1 here is going to be 7 cosine t e to the 4t times 4. Okay, so that's what I've written here. 7 cosine t e to the 4t times 4. Okay, dot with r2, and this is what r2 was. Well, if you work out the details, if you do this dot this, okay, so you do 7t times 2t plus sine t times 5t to the fourth plus e to the 4t times 0, and so forth, and you do the dot product of these, and you simplify it down, turns out you get this, which is the exact same thing as this. Okay, and we knew it would, as long as this product rule really holds, these left and right hand side really should be the same. Okay, we have one more thing to do in this section. This is a theorem, and this theorem is going to be important for something a little bit later. But I want to make sure you really understand what this theorem is saying, and don't over-interpret this theorem to say something it's not saying. Okay, this theorem says that if r of t is a differentiable vector-valued function, so differentiable just means it's each of the component functions are differentiable. If r of t is a differentiable vector-valued function in 2 space or 3 space, and if the norm of r of t, okay, the modulus or magnitude or norm of r of t is constant for all t, then r of t and r prime of t are going to be orthogonal. Okay, r of t dot with r prime of t is 0. So they're orthogonal vectors for all values to t. Now this is not true at all for most vector-valued functions r of t. But for vector-valued functions that have this property, and I've underlined it red, that the norm of r of t is constant. So what would that mean? Let's say we're in 3 space. What would that mean to say that the norm of r of t is always constant? Let's say that the norm of r of t is always 5. Okay, so in other words, no matter what your input t is, you get an output of a vector that always has a length of 5. Well, what does that mean? Well, look at the sphere of radius 5 centered at the origin. This vector-valued function is going to be a curve that lies on that sphere. Okay, because the norm, the length of no matter which input you put in, your output would always be on that sphere. So this condition that says that the norm of r of t is constant would mean your points always lie along this sphere. Now in 2 space, it would mean all of your outputs always lie along a circle. Okay, no matter what your input t is, it's always going to be traced out along a circle. But notice in 3 space though, what this is saying is that if you look at the tangent vector at any particular point, if you look at the tangent vector, it's going to be orthogonal to the vector that goes out to that point. So r of t and r prime of t are going to be orthogonal, perpendicular. So in other words, the r prime of t is not going to be shooting out this way or popping into the sphere like this. The r prime of t is going to be actually tangent to that sphere, which is going to make it orthogonal to this vector. Okay, so no matter how this curve is being traced out, as long as it's being traced out along the surface of that sphere, the tangent vector will always be orthogonal to the r of t. Now, again, this is going to be a useful theorem for something for us later, but why is this true? So first of all, I want you to remember that v dot v, for any vector v dot v is the norm of v squared. Now, I never actually showed that, but why is that true? Well, if v, let's assume we're in 3 space here. If v is v1, v2, v3. What's v dot v? Okay, what's a vector dot with itself? Well, it's v1, v1 plus v2, v2 plus v3, v3. In other words, v1 squared plus v2 squared plus v3 squared. By the way, notice that's never negative. Now, if you do u dot v, the dot product of 2 different vectors, you can get a negative number, certainly. But if you dot a vector with itself, you'll never get a negative number. In fact, what you're going to get is the norm of that vector squared. Because notice, what's the norm of this vector squared? Well, the norm of v1, v2, v3 is the square root of v1 squared plus v2 squared plus v3 squared. And if we square that, the square root and the squared go away, and we just get v1 squared plus v2 squared plus v3 squared. So in other words, v dot v was equal to this, but the norm of v squared was also equal to that. So v dot v is equal to the norm of v squared. That's an important property of dot products. Okay, now how is that going to help us? Well, if we have a vector-valued function, if you input the t, you're going to get output of a vector r of t. Well, the norm of that vector squared will be like that vector dot with itself. So the norm of r of t squared is going to equal r of t dot with r of t. Okay, so it turns out that the derivative of this, the derivative with respect to this, with respect to t of this, is going to equal the derivative with respect to t of this. But how do we take the derivative of a dot product? Well, we just talked about that in the last, when we talked about the product rule, right? We do the first function times the derivative of the second, and then we do plus the derivative of the first times the second. So the point is you're going to get r of t dot dr dt plus dr dt dot r of t. So in this case, the r and the r, those are the same. And before we had a r1 and a r2. But these are the same function. So notice this is the same as this. Okay, r of t dot dr dt is going to be the same thing as dr dt dot r of t, right? Dot products are commutative. So what you really have is two of these things, two of the r of t dot dr dt. Now remember though that the norm of r of t, quantity squared, is constant. Now why is that the case? Well, because the norm of r of t is constant. So that's the thing we were assuming. The norm of r of t is constant. So let's say it's always 5. Well, then the norm squared would always be 25, right? That would be constant as well. So what's the derivative though of a constant function? Okay, if this is always constant, it would be 0. So the point is that dt of this thing would be 0. Well, if this is equal to 0, but it's also equal to this, then 0 is equal to this. Right? So the point is 2 times r of t dot dr dt. This is 0. Okay, and you can divide both sides by 2 now, and the point is you get r of t dot dr dt is 0. Or in other words, r of t dot r prime of t is 0. So in other words, r of t and r prime of t are orthogonal. Okay, and you can kind of see this, and if you think about this as if the curve is being traced out along the surface of this sphere, so maybe think of like a tennis ball or a baseball, they have a curve on there. Okay, if you looked at all the points that go from the origin to the points along that curve, and you looked at the tangent line, the tangent vector, or the tangent line, is not going to pop out here or pop into the sphere. The tangent line is going to go out this way, so that tangent line is really tangent to the sphere itself, and so in other words, this vector will be tangent to that vector. Okay, so last video we talked about vector valued functions. This video was about the calculus of vector valued functions. So we did limits and derivatives and integrals.